Oh, by the way, did everybody find the handouts for related rates on Google Classroom? I'll show you where they are real quick. So if you didn't find them, they're under handouts, course information and resources on your Google Classroom page. And then if you go, you can just follow the links here. What is this? Unit 3. So there they are. Guidelines for solving related rates problems. That's the one you want right there, right? Okay, so you might even want, if you haven't done it yet, you might even want to just print one of those out. Okay, here we go. So related rates. We left off, I believe, we looked at some examples last time, and I think we left off, we left off on this guy. No, we didn't. We finished that guy. We left off on this guy, right? We were trying to find the rate of change of the angle of elevation of the camera. If this camera down here at ground level is tracking the rocket as it's ascending straight up at 10 seconds after liftoff, right? And they gave us, remember on this one, they gave us a position function. This is the height of the rocket. And so at time t equals 10, that identifies the frame in our video that we're wanting to scrutinize. If we plug 10 in, we get an answer of 5,000 for our height. So when we're creating our snapshot values, let's just go back to this for a second, right? Step 1, we're trying to identify for our one frame that we're asking about in the video. We want to identify what the values are of all of the variables and the rates that we can. We want to identify any information we're given about that stuff. And then also we want to identify maybe what is it we're trying to find on that list. Okay, so for us, here's our picture, right? We know that S, which is the height, is 5,000. And that's really the only variable that we're given, isn't it? We're trying to find theta dot. Okay. Now we have some other information here about this triangle. We know that the horizontal distance between the camera and the rocket is 2,000 feet, but we're not going to include that in our snapshot values. That just stays on our picture, right? Because that's not a variable. That's a constant. It never changes. We only want to put the values of the variables and the rates up here. Okay. And so we decided then that if we wanted to come up with, if we look at the variables that we've got in step 1 in our snapshot, we've got S's, which is the height, and theta, and we want to come up with some static equation that relates those two variables, right? Remember, we're ignoring all the dots here. We're ignoring the rates, and we just want to come up with an equation, a pre-calculus equation, right? This is not fluid or dynamic. We just want to come up with a static equation that relates those things. And this is a right triangle trig issue, right? We've got this, we build this right triangle where the base of the right triangle is 2,000, the height is S, and that angle is theta. So this is, we'll use SOHCAHTOA stuff, right? This is a tangent issue. So tangent of theta equals opposite over adjacent. So that's S over 2,000. And we left off, there's our step 2, right? We built our parent equation. And then we left off on step 3, using the chain rule to differentiate with respect to t. I think we may have even finished that, right? So we got the derivative of tangent theta with respect to t. Well, this is a chain rule issue, right? The derivative of tangent of something, tangent of hand, is secant squared hand, times the next link in the chain would be the derivative of what's inside the tangent with respect to t, and there's our theta dot. So we get secant squared theta times theta dot equals S dot over 2,000, okay? We're trying to find theta dot. Okay, so could we add, what are the things that we know here? Well, we don't know theta in this equation. We're trying to solve for theta dot now, and we don't know S dot. But could anybody tell me how, given this information we've got up here and the fact that t equals 10, could we come up with a value for S dot that we could add to our snapshot values? Any suggestions? Andy, you're shaking your head. You have an idea?
Would you just take the derivative of S?
Okay, good. We could differentiate S with respect to t, couldn't we? Right? So we've got S as a function of t. If we differentiate that with respect to t, we get S dot equals what, 100t? So for our value of t, we get 1,000. So that's our snapshot value. Everybody agree that's our snapshot value at t equals 10? That's our snapshot value for S dot, right? Okay, so now we've got almost everything we need, right? We've got S dot, but we don't have theta. If we were going to solve this thing for theta dot in order so we can plug and chug and get our answer, and remember that's the last step, right? We isolate the variable that we're trying to solve for and plug and chug. Meaning we just substitute values and simplify, right? So our very last step then would look like theta dot equals S dot over 2,000 times 1 over secant squared, right? Well, what is the reciprocal of secant from trig class? One over secant theta equals what? Cosine. Yeah, exactly, right? Because secant and cosine are just reciprocals of each other, right? So then we end up with cosine squared theta here. And so there's our answer, but the problem is we don't have a theta in our list of snapshot values. So what are we going to do about that? What are our options here? What are our options here? What do you think? Madeline, you have an idea what our options are?
No, not really.
Okay. Anybody want to chime in? We don't have a value of theta. So we could try to add a value of theta to our snapshot values. I mean, we could do that, right? Because we know for our snapshot value, we've got this triangle up here. At our snapshot at t equals 10, we know that this distance is 2,000 and this distance right here, right, this distance right there, for our snapshot value is 5,000. So we ought to be able to solve for theta there, right? Everybody agree we could, and we could get an answer. We could just say something like theta equals the arctangent of 5,000 over 2,000. Everybody agree? Right? Remember, if we have the statement tangent theta equals 5,000 over 2,000, right? If we plug 5,000 in for S. Well, if I want to solve for theta, I just take the arctangent of both sides. So one thing I could do is just define theta as that. That's just a number. Theta equals the arctangent of 5,000 over 2,000, which is the same as the arctangent of 5 halves, right? Okay, everybody agree with that? We good with that? That's one way to do it. I think there's a better way, though. There's a better way to do this. I want to introduce you to the wonders of reference triangles because they are very helpful critters in math. If we can build a right triangle relationship like this, then effectively we've got a reference triangle. And we can define any of the trig functions in terms of ratios in that reference triangle. Okay, so let's just do that part. So let's just focus on Here's our reference triangle. Let's just focus on this reference triangle. Oops. And this is all coming from the statement tangent of theta equals 5,000 over 2,000 for our snapshot, right? This is a snapshot value. So if we build this reference triangle, it's pretty simple. There's theta. This is 2,000. This is 5,000. And by the Pythagorean theorem, we can find the other side of this triangle pretty easily, right? It's just the square root of 2,000 squared plus 5,000 squared, whatever the heck that is, right? So 2,000 squared, what are we going to get here? We're going to get 2,000 squared is 4 million. 5,000 squared is 25 million. And so we get the square root of 29 million. Everybody good with that? Did I do that right? I think I did. Okay. So there's our reference triangle. Right now, all we have to do, if I want to define any of the trig functions, I just use their SOHCAHTOA definition, right? We know tangent is opposite over adjacent, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and then the co-trig functions are just going to be the reciprocals of those, right? Like if I wanted to do, or not co, I mean if I did the, sorry, not the cos, if I did the secants or the cotangents or the cosecants, you know, those are just reciprocals of those SOHCAHTOA relationships we just identified, right? Okay, so then all we'd have to do here is I could use my reference triangle. I don't know what that is. I could use my reference triangle to define cosine theta in terms of a ratio reference triangle. So I just end up then with theta dot when I plug and chug here. Look what I get when I plug values in. I get theta dot equals S dot, which we identified as 1,000 over 2,000 times whatever the cosine of theta ratio is squared. Well, based on my reference triangle, Daisy, what's the ratio here for cosine of theta?
Which one is cosine again?
The cosine is, remember, cosine is, here, let's write it down. If we've got SOHCAHTOA, cosine is what divided by what?
Adjacent over hypotenuse.
There you go, adjacent over hypotenuse. So that's going to give me 2,000 over the square root of 29 million. And I could even just write that, if I want to just write that as the square root of 2,000 squared plus 5,000 squared. Right? I can leave it like that if I don't want to process that. I never really had to make that a 29 million. I could have just left it like that, squared, right? So there's, if I plug all this into my graphing calculator, well, I can get an answer for this, right? I'm just doing that. I'm just evaluating that expression, and I get something like 0.0689, blah, blah, blah. Something like that, right? Now, what are the units going to be? This is important. What are my units going to be? What do you think? Caleb, what are my units going to be here? I'm calculating theta dot, right?
Would it be degrees?
So degree, and what are we measuring? It looks like we're measuring, time is always measured here in seconds, isn't it? And so the question is, you're saying degrees per second?
Yes.
Okay, so let's say hypothetically, though, that John Degree, the inventor of the degree, that's probably not true, but I made that up. John Degree, let's say that he arbitrarily decided to break up a circle into 720 degrees instead of 360 degrees. That would change your answer, wouldn't it? That would have a different meaning then. Right? Do you think the math gods should be dependent on what John Degree chose for his arbitrary size of a degree? I don't. So it can't be degrees, can it? What do our units need to be? Anybody got an answer?
I mean, you could put it in radians, but I mean, technically, you could, like, originally they may have defined pi as twice as big as the radian.
No, they couldn't. They couldn't define pi as being twice as big because pi is a fundamental constant. Pi is the ratio in a flat space. Pi is the ratio of the circumference to the diameter of a circle. So there is no, Jim Radian didn't have any choice when he defined the radian, right? That was, or actually that was Jane, I think. It was Jane Radian. She didn't have any choice when she defined the radian as being what it is because it is a fundamental constant. It's a geometric, it's constrained by the geometry of a flat space, right? So you see the difference. There's a big difference there. Radians are not arbitrary, degrees are, right? If you think about, I want to take just a second and reinforce this point because this is a pretty big point. Ooh, that seems bright, doesn't it? So if we take a circle here, so there's our circle. If this is a unit circle, right, we know that the circumference of a unit circle, because the circumference of a circle is just 2 pi r, right? So the circumference of a unit circle, the circumference is 2 pi times 1, so it's just 2 pi. So look where the radian came from. The radian didn't come from, it's not actually, we define a degree as a unit of angle, right? An angle is just the distance, or is the angular distance subtended by an arc, right? But we think of it in terms of just an angle. Well, that's not what a radian is at all. A radian is actually not defined as an angle. A radian is defined as, it's not technically defined this way, but we'll say it this way. You could think of it as being the distance that an ant walks along the unit circle, right? Because the circumference of the unit circle is 2 pi. So if an ant walks this far, maybe that ant has gone, let's just say he's gone a distance of 1/12 of the distance around the unit circle. Well, then that's going to be, he's traveled a distance of pi over 6, right? When he's gone a distance of pi over 6, well, that does correspond to some angle, right, on the unit circle. And so we can correlate that with an angle, can't we? Right? So radians, we can take radians to mean an angle, and it works fine. Okay? But you see here how radians are fundamental. Just a little rule of thumb, because this comes up in physics a lot. Whenever you're solving for a naked angle like this, right? You're solving for an angle without reference to anything else. you always have to assume radians unless there's some other specific information in there where there could be contexts where we're told we're measuring things in degrees, but then that changes the rest of the problem if we do that. Okay, everybody give me a 1 to 5 on what I'm saying there. I just want to make sure you make that connection because that's a really important thing to file away in the back of your mind.
I was just thinking that, like, for instance, degrees is a standard. So, you can assume that there's 360 degrees in it.
Right.
The same way that pi is a standard. So you have to assume that, what I'm saying is if you assume that someone knows the definition of pi to be 3.14 was twice as big, if pi was twice as big, like the symbol pi is twice as big, then this would just be pi r, and then there would just be pi radians.
Right. Okay. But once again, pi is, if you defined pi like that, and I think that's actually called tau, then you would know that the unit circle changes. If we're talking about the unit circle in terms of tau instead of pi, well, then the unit circle changes a little bit, right? And so we would have to make corresponding changes to our answer. But those are fundamental changes. Look, there's nothing up in this problem here that tells us anything about the way theta is being measured, right? And so we have to assume any answer we get for theta here has to be in radians, just has to. Now, we could convert that to degrees if we wanted to. That's fine. We could multiply our answer by 180 over pi and convert it to degrees, but then we've made some conversion from the fundamental radian to some arbitrary unit that happened to be degrees, right? Anybody see that? I mean, there's no freedom here. This has to be in radians. There is no choice. Radians make sense because radians are fundamental. Right? If we measure theta here in terms of this reference triangle, it definitely has to be in radians. And I guess at this point, that's all I really care that we'll see this stuff enough throughout the year that you're going to have a good, you'll internalize this conceptually and you'll be more and more comfortable with the concept I'm talking about. But for now, you just need to know that in situations like this, where you're not sure, where there's no specific angle given, this is our answers in radians for sure. Okay. All right. So then if we, this is our answer, right, for theta dot. And I just processed this on Desmos. If we round this to, if we use, how many places here? I guess let's just assume that we've measured this stuff up here to, 2 decimal places or something, right? Or 3 decimal places. So then we end up getting theta dot. Oh, that's a bad color. Theta dot equals 0.06. We'll just round one more. 0.69. How about? Radians per second. And radian is really unitless. It's not like it's not even technically a unit, but it tells us how we represented those angles in radians. Okay?
Mr. Webb?
Yeah.
Could you go over real quick how you got cosine squared theta to go to that 2000 over the square root squared? I don't really understand
How we got this part right here?
Yeah.
That's from our reference triangle, right? Because our reference triangle corresponds to the values for our picture up here at our snapshot. Okay, at our snapshot.
I get where the values come from, but how did the cosine squared theta turn into that?
Because cosine is, by definition, cosine is adjacent over hypotenuse, right? So if that's theta, the adjacent side is 2000, and the hypotenuse is just the square root of that squared plus that squared. I could have just plugged in 29 million down there instead if I wanted to. Square root of 29 million.
Yeah, okay, great.
Okay. Either one would work. So give me a 1 to 5 on that, everybody. Okay. These take some practice. You just got to crank through some of these. They're fun to do. Boy, they're really rewarding when you get them right, because they're these are kind of real problems. I mean, you got to do some work on these things. Okay, I'm going to skip this one for now. We just did a trig one. Let's move on and let's try this one. This is a really good problem to do. There's an important moral, and this might take us the rest of the period to do this, to get through parts I want to on this. But you got to really just kind of regather get your thinking cap on, and you got to really just focus here. Just focus. Don't write any notes down. I'll make all the notes available. Just focus on this stuff. So at a sand and gravel plant, sand is falling off a conveyor and onto a conical pile at a rate of 10 cubic feet per minute. Tells us that the diameter of the base of the cone is approximately 3 times the altitude, or the height. At what rate is the height of the pile, so that's the altitude, at what rate is the height of the pile changing when the pile is 15 feet high? Okay, so we'll start off here. I'm going to give you a couple things here. I'm going to give you, first of all, there is our formula for the volume of a right circular cone. Okay, 1/3 pi r squared h, where r is the radius of the base and height is obviously, that's the altitude or the height, whatever you want to call it. Okay, here's our picture maybe that we get from this. Okay, so we want to be able to identify snapshot values. So help me out here. What are the values that were given for this snapshot? Ember, tell me one snapshot value that I could add here.
It's falling off at 10 cubic feet per minute.
Okay, so what am I going to label that? What is that value? I can't just write the value down. I have to set it equal. I have to know what value is that.
I'm not sure.
Okay, here's how you can tell. Look at the units. We have cubic feet on the top per minute. So that's units of what divided by what?
Distance over time.
No, cubic feet's not distance. What's cubic feet? No, that'd be square feet. Volume, there you go. So this is units of volume per time. So what must that be then?
I don't know. I'm blanking.
Okay, that's fine. That's fine. So let's see. Help me out here, Emma. What's that going to be?
That's dV over dt, so is that v dot?
Okay, v dot. Good. It's dv dt, right? So that would be v dot. V dot is 10. And I'll add the units here. We don't need the units, right? But I'll add them here just so we can kind of make a correlation to the description. Cubic feet per minute. So there's one thing we're given. Johan, what's another thing, another snapshot value that they give us?
15 feet.
Okay, what is that?
Height.
Yeah, height, isn't it, right? It's 15 feet high. So the height of the pile is 15 feet. And while you're at it, Johan, what are we trying to find here?
The rate that the height of the pile is changing.
Okay, so what would I call that?
DH, or I guess H dot.
H dot, right? DH dt, but H dot is that's the notation we're going to use, right? So H dot equals, well, that's what we're trying to find. So that's my question mark. Okay. All right. So there's step one. We identified the snapshot values. What's step two? What's step two here, Natalie?
Coming up with a parent function.
Okay, good. We need the parent equation, don't we? Right? Well, we have that, right? That's the volume of the cone. Everybody agree? Okay, so we could take the volume of the cone here, right? And we have our picture, the volume of the cone, and we should be able to differentiate that, right? So there's our parent function. And now, okay, so we did that. We created a parent function. Let's make this a little bigger. How about? And so now we should be able to differentiate that for step 3 implicitly with respect to t, right? Okay, what are we going to get, Lily? If I differentiate this with respect to t to get v dot,
So are we just differentiating that equation, or are we plugging in values?
okay, so you can't plug in values until after you differentiate, right? What would the problem be with that? If I tried to plug in my snapshot values before I differentiated, we would be throwing a pretty big curveball to the math gods, because what would be the problem there? What's the derivative of a constant? Kirsten, what's the derivative of a constant? 0. Yeah, see, that'd be a problem, right? Because if I plugged in the values first, I would just get v dot equals 0. Well, that's clearly not the answer, right? So we can't plug those in until after we differentiate. Okay, so we just have to take that parent equation with the variables in it and differentiate. So I've got this 1/3. That's a tough one, isn't it, though? What makes that a tough one, Lily?
Is it because of the pi?
No, pi is just a constant. If I wanted to, I could even take that 1/3 pi. We'll just call it a pi over 3, and we'll just pull that out front and only differentiate that stuff, right? Because the constants we can always pull out in front of a derivative and forget about, okay? But what's tough about the derivative of r squared times h? I mean, it's not horrible. Maybe I'm making more out of this than I should, but it's not super convenient, right? Because it's a product. We got to use a product rule here. Okay, so let's try that, Lily. This is your job here. You got to differentiate this with the product rule, right? So we've got r squared times h. I get first times the derivative of the second plus the second times the derivative of the first. So what's that going to give me?
So it's uv prime plus v prime u, right?
There you go. So r squared times.
Then what is the derivative of just h?
Okay, so we're differentiating with respect to t, aren't we? Right?
Oh, so would it be h prime?
H dot, we'll say,
Okay.
because we're differentiating with respect to t. Okay, good. Plus
H.
2r. I'm differentiating with respect to t.
Oh, dot then?
Yeah, good. So I'm going to need an h times a 2r dot. Okay? So there it is. There's my v dot, right? What's the problem with that, though? Look up here at my list of snapshot values. We got some holes, don't we? There's a lot of things that we don't know. We don't have values for up here. If we're solving for h dot, I'm not even going to go through the hassle of isolating h dot, but would you agree if I isolated the h dot, I'm going to get v dots and r's and h's and r dots in my answer in some form or another, right? Well, I don't have very much of that stuff. I only have v dot and h. I don't have an r or an r dot. So what are my options?
You can find the R by just plugging H into the equation.
Okay, so I could find the r because they give us some information about that, don't I? Or don't they, right? So I could maybe do something like this. They tell us that the diameter of the base of the cone is approximately 3 times the altitude. So let's take that piece of information right there. I could turn that into maybe the equation, a secondary equation, right? That's relating my independent variables, r and h, diameter of the base, so that's 2r equals 3 times the altitude, so 3h, right? So I could solve for my value of h, or of r here, by just plugging in my value of h. I could add an r equals if I wanted to. I could differentiate this with respect to t, and when I get a value, I could relate the r dot to the h dot. This is starting to get a little bit cumbersome, though, isn't it? This is fortunately for us, this is sort of a dead end, because look what they say down here, or look what I say in my instructions. When we create a parent equation, there's a really important part of this. Look at this part right here. The parent equation should end up as a function of a single independent variable whenever possible, right? Well, we could do that, right? We could do that. We could instead, how about if we just used this equation up here, this secondary equation? So we could rewrite this. If I solve for r, I get r equals 3/2 h. I could just make that a substitution equation, couldn't I? Right? I could just plug that value in for r, and then I would have the volume as a function of only h. That is huge, right? That's what we want to do. We always want to try to write our parent function as a function of a single variable, okay? In fact, we're going to have to this year. This class might as well be called Calculus of a Single Variable, because we're not doing multivariable calculus yet. That's later on down the line. I mean, it's not that we couldn't have done this problem the way we did, but it would have been a lot of extra work. So let's go back to the drawing board on this one, and let's try the same thing. Let's try the same thing with using our using our trick. Not really our trick. We're just going to write our parent equation as a function of a single variable. Well, we already had, let's just summarize this stuff here. I guess I didn't really need to do this whole thing. We found v dot equals 10. I won't even put the units down. The units will just keep distances in terms of feet, time in terms of minutes. And we had, what was the height? 15. And we're trying to find h dot. Okay, so our parent equation, here's our parent equation. There's our parent equation, but we're going to use, just like we had before, we're going to use this other piece of information they give us. And this is really, sometimes we call this it's a secondary equation, but sometimes we call this an equation of constraint, because it's constraining the solution that we're going to get to this. So it has to fit this condition. You don't have to call it, we will call it that when we get to optimization problems, which is later on, but we'll just call it a secondary equation. So the diameter of the base is approximately 3 times the altitude, right? So we have this other equation here, our secondary equation. What was it again? I guess we're calling this, doesn't matter. We're calling this, well, I called it X and Y, but we've already started calling it R and H. So we'll leave that as H, and that's R. 2R equals 3H. So R equals 3/2 H. There's our substitution equation. We'll plug that in there. And look what happens to our volume then. Our volume equals pi over 3 times the quantity. For R, we get 3/2 H squared times H, which ends up being what? If I square all that stuff, I'm going to get 9 on the top. I could cancel one of those 3's with each other, right? So I'm going to end up getting 3 pi over 4 times H squared times H is H cubed. Just check my work on that too, but I'm pretty sure that's right. So that's V. Okay, but we could even call that now, we could do one step better. We could call that V of H because it's volume as a function of height only, right? Give me a 1 to 5 on that. You see the huge advantage of that. Look how much easier that's going to be to deal with. Very simple derivatives, right? The calculus is easy. We have fewer variables to work with. So do you see the advantage there of rewriting this, of solving for R as a function of H, making that substitution? So now we get volume as a function of only a single variable H. Okay? So from here on out, this isn't going to be a big deal. We've got our parent function that we're going to differentiate. V of H equals 3/4 pi or 3 pi over 4 H cubed. So what is V dot then? What am I going to get for V dot here, Sydney? If I differentiate this with respect to T.
I'm not sure.
So I've got this constant out front, right? What's the derivative of H cubed with respect to T?
Say that again.
So we can ignore the constant for a second. What's the derivative of H cubed with respect to T?
Oh, 3h squared h dot.
There you go. Times my constant. Just gives me 9/4 pi H squared H dot, right? So I differentiated with respect to T implicitly. Now the last step is just for me to isolate the H dot and plug and chug. I'm trying to solve for H dot, right? So we end up with, if I isolate the H dot, I've just got to multiply each side by the reciprocal of this, right? So I'm going to multiply by 4 divided by 9 pi H squared. So I'm just going to get 4 V dot divided by 9 pi H squared. I know all those values. I can plug and chug. That just gives me 4 times, was it 10? Was that my V dot? Yep. 4 times 10 divided by 9 pi times H, which is 15 squared. So what's that give us then? 40 over 9 times 225 is going to be 1225, I think. No, that's wrong. What am I doing? 2025? Somebody do that real quick.
It's 2025.
2025, yeah. 2025 pi on the bottom, and that's it, right? That's my answer. What would the units be? What would the units of H dot be here? Sam? Looking at the original problem, what are the units going to be for H dot?
I'm not sure.
Well, what are we measuring? It's just going to be units of length or height, right? Divided by units of time, right? That's what H dot would be. Units of height divided by units of time. Well, what would the units of height be? What are we using for our units of distance up here? Feet. Yeah. What are we using for units of time?
Minutes.
Minutes. So feet per minute. And that's an exact answer, right? Okay, I'd drop my pen if they weren't so expensive. I don't want to break it. Okay, give me a 1 to 5 on that. Does that make sense? I mean, no one's going to show me a 5 here probably. There's a lot of stuff to digest. Okay, but we're just chugging through those 4 steps. Okay. All right, what do we got next? Okay, this is just in the notes. Maybe I don't really need that page. I guess I already got, that was the last page. Okay, let's just set this up. I mean, this is where we just got to keep doing examples. And then you guys will be working on homework in between. And you'll come back and we'll just do more examples. And within a few days, you'll be feeling good about this. But next step is do some homework. Let's maybe try something like this. So once you guys work through this with me, 40, oh, we only have 2 minutes, don't we? No point. Okay. All right, I'll call her. I'll put the assignments up. Those will be available, I think, no later than the end of lunch. Those will be available. So you can start in on those. I'll give you a little lead time on them. I mean, these take a little time. I get that. Okay. But I consider this to be a pretty important section.